Hi everyone, welcome. Today we're going to have our special guest, Hyrum Anderson, who worked at Microsoft and now is working at Robust Intelligence and came here to visit Israel to present at the BLUEHAT conference. Hyrum, welcome.
Thank you. Thanks everybody for joining. So if anybody is attending BLUEHAT, this is a different talk with maybe 50% overlap. So apologies if you have to also attend the BLUEHAT talk and suffer through some of that. Briefly, I want to I'm just honored to be here, and I'm going to talk today about supply chain risk management in machine learning models. But before I do, I want to just give a brief introduction to Yaron's company, who's sitting right next to me, who is from Tel Aviv and he's home now.
Yes.
So I feel really fortunate to be with Robust Intelligence, who is just leading this space in AI risk management. And Yaron and team have done a wonderful job of building a foundation. This is a highly acclaimed and recognized company. I feel lucky to be a part of it. And we have some amazing customers that have helped to guide our path. Essentially, the company started with Yaron and Kojin, who was a student doing undergraduate research in robust machine learning at Harvard. And Yaron, frankly, got sick of academia because he could make a bigger impact here at Robust Intelligence. So
yeah, no.
Okay. So here we are. I want to just like AI, as it is being adopted everywhere, is taking on a new form of software. It's changing the way we do software development. And with that come special kinds of failure modes that are on top of what the traditional software failure modes already provide for us. And the ones that, like the way we break these down is we like to lump them into these categories of operational risk. So that's, when I deploy my machine learning model, is it overfit to a pristine data set that if it encounters image blur or Gaussian noise, whatever, will it fail, right? There's security and privacy risks. Those include what would I do in the presence of an attacker trying to specifically subvert my system, and there are ethical risks, and all of these are important. But today, I want to specifically talk about the security and privacy elements. And the key thing, the key takeaway here is that AI is software, but it's more. It's data and it's model. And so there's things that you inherit in the risk from the software supply chain, but there are new things that come with the supply chain risks in the model itself. So I'm using this chart here as my outline slide to talk about the different kinds of risks, and we're going to go through them. So think about everything that you do at Microsoft to build a model, or to maybe use a third-party model from another team at Microsoft, or from a third party like like Hugging Face. We get data often from third-party sources, sourced from the internet, sourced from a different team. We have models that come from there, and then those come with their own specific risks. And then of course whatever model we either build or fine-tune or inherit have their own kinds of risks. So I'll touch on, this is my outline, we'll touch on each of these today. So first is that, I want to just set, we're going to come back to kind of the machine learning specific kind of evasion. I think everybody has seen this image that has now become the lingua franca of adversarial machine learning failure modes to iconify that machine learning can be fooled in simple ways. But that's like here. That's the end of the pipeline. I'm going to rewind and go to the beginning of the pipeline. So the first few minutes, I want to just review some recent work that we have done with collaborators at Google and ETH Zurich and NVidia in data poisoning. So first thing. So one thing that is useful to have in your mind is kind of a rule of thumb, and that is that based on I guess 18-month, 2-year-old work from Nicholas Carlini, showed that he did some experiments to show to measure what fraction of a data set must I control in order to appreciably poison the model so that it fails in some way. Do you remember this paper? So the bottom line is that for a bunch of different popular data sets at the time, and for a set of different poisoning rates, you could have a failure rate. So this means, for example, with 0.1% of the data set controlled of CFAR10, I can poison such that 7 of 8 out of tests fail, of models fail, right? So what you should have from this is just, if I can control 0.1 of a data set, 0.1%, that is enough, academically speaking, for me to poison a model so that it will not perform in its intended way. So given that as foundation, now one asks, like, okay, so how do you actually get control of 0.1% of a data set? Especially when we're talking about web scale data sets of massive scale, 0.1% is a huge amount of data. But this is where our joint paper work comes in. And I just want to, from the outset, like I am, I'm very generously listed as, the 6th author here. I think everybody on this author list did much more work than I did. I'm again, lucky to collaborate with really smart people. The other thing I'll note is that, a talk is an advertisement for a paper. And I'm not going to go into all of the parts of this paper. I want to tease you and give you the highlights. And I also suggest that you go listen to Nicholas Carlini talk about it, or Will Pierce talk about it. I think he'll do Black Hat. Nicholas will do Usenix. So this will just be a highlight tease for this. Okay, so the paper is about how do I practically control enough data so I can appreciably poison the model. And it's like very, very simple, right? So we present 2 attacks that I'll cover today on the data supply chain. So number 1 is what we call the split view attack. And it's very simple. Modern data sets are too large for me to put into a CSV file. So instead, as a data set provider, I give you a CSV file that says URL, label. However, domains expire. And so this attack, all it does is it looks through the URLs, searches for expired domains, and does domain takeover. And then I can control what, if somebody asks for a specific resource on a domain, I can control what that person receives. That is the essence of the attack. The problem is here because the vulnerability is because that when somebody gives you the CSV file, there is no cryptographic hash today, or at least at the time of our paper, no cryptographic hash saying that when you get this resource, it should have this hash. So you could go get anything. And what we've done is the bottom line here is that in very, very large data sets, so this is 2 times 10 to the 9th, right, entries in this data set in Lion 2 billion. We can find domains that have expired that account for 0.2%, almost 0.3% of the data set, and buy them if we want to, right? So here are all these web scale data sets, Lion, which is now kind of the standard for image training at its various sizes, as well as a lot of the other popular data sets that have come recently. The upshot is that for $60 US, we can buy enough domains to poison 0.1% of these giant web scale data sets for $60 US. It's really interesting, actually. Common Crawl is like the time machine. If everybody used this, it captures the internet and archives it. And what's really cool is they've put this on a in Amazon in this framework that allows you to very, very cheaply analyze it. So actually, for 84 US cents, we were able to analyze 10 years of these domains to figure out which ones were the most popular and were expired. So the reconnaissance was literally pennies, and the attack was under $100. And We actually did purchase these domains. We purchased domains, and we did not poison. We actually, when somebody would visit the site, we'd let them know that this was for research purpose, but we would track them. And so what you're seeing in this figure is well, I'll show you the next figure actually, is we watched people as they would download data sets as they pass by. The thing that we often forget is from our computer science 101 class is that an int const star is different from an int star const. So we treat these data sets as if the URL is pointing to a constant resource, but in fact, it's a constant identifier pointing to a mutable resource on the end. So what does this look like? As we bought these domains, we watched what people were doing. We can actually track by their, their user ID and their IP address, other things. We can see individual crawling people do their stuff. So what does this mean? Just take a look at a few of these. Like some people, so the x-axis is time, the y-axis is what resource are you grabbing. Some crawlers like the pink do this very, very fast. They zip through the whole data set. And how do we know this is not a random crawler? Well, it's because they're visiting the data set in order, right? They're doing it as they're reading the lines of the CSV. Some do it very, very slowly, like this blue line, and some do it in parallel. So like these red lines here are people chunking, like sharding up the CSV file and then visiting those domains. We control 8,000 of the resources among the billions and billions, but we can this is a sampling of that data set. So given that we can actually track people, this also opens up another attack. What it means is that I can choose to give Iran the correct data, but choose to give Guy the poison data, right? I can very specifically poison specific people looking for these popular data sets, which becomes now very hard to trace, right? If Iran has a model he's trained and Guy has a model he's trained, and they're like, even if you had the same data set, the models don't have the same hash or maybe the same performance. So it'd be very difficult to know if you've been poisoned unless you looked at the data and knew kind of where to look.
That's a question. When you say poison the data, so that means, say, inserting a certain bias or something that you already know what the outcome is going to be? Because just to randomize the images doesn't really, someone who trained the data and they'll just get something which is corrupt.
Great point. So I've said poisoning very cavalierly. Yes. There's label flipping poisoning. This is out of scope. Remember, the CSV file has the label. What we're doing is we're modifying the content of the image, and the preferred thing is to the kind of poisoning you like to do. This is all for. In fact, in some sense, much of this is actually unsupervised. And in those poisonings, what you like to do is like create a beachhead across the future decision boundary. So you deliver samples that are all similar to each other that move into the other class that is a really effective poisoning. So this is not something we actually did in this research, but if you go visit Nicholas's previous paper, he'll show you, like, if you want to get this 0.1%, this is how you do it.
But does that mean, though, when I would take the data, even if it's incorrect, and I'll train my model in the end, I will see that it's using regular tools, I can identify if there's biases, if there's things that are incorrect in the data, surely. What defines more as a poisoning and something which just gives me, give me a model which is incorrect?
Yeah, and again, that's like another class. If I'm poisoning, is it kind of indiscriminate to cause the model to fail for all inputs, or is it very targeted so that for a specific input? And in the latter case, maybe that's something where that would differ. It's like general bad performance versus like a backdoor, right?
Is that something which is that can be done, like to create something like that?
Yes, absolutely. Yep.
That's good.
Okay, so this is attack number one, and we have notified the data set providers, and the vast majority of them have now done, they've computed cryptographic hashes and now released the hash so that when you ask for a resource, you yourself can compare. as a side note, it turns out that if you are computing millions of cryptographic hashes, your IT provider may think you're also mining Bitcoin. So it's something to be aware of. This happened to Nicholas at Google, was flagged for being a Bitcoin miner. Attack number 2 is also very simple. And this is what we call a front running attack. And primarily it just applies to Wikipedia. And what this is just takes advantage of the fact that when Wikipedia, so first of all, Wikipedia is an awesome data set. It provides lots of structure, lots of text that's well formatted. It provides media with it, and it provides it across many, many languages. So this is a gold mine for generative models, for translation tasks, whatever. So this is very heavily used. The thing to note is that Wikipedia never intended it to be used for machine learning. It's for human consumption. So this is not at all meant to critique Wikipedia. I just want to point out that what Wikipedia does is every month or so, they will archive their entire encyclopedia into a file that you can download. And what we did is, what my co-authors did is they watched, when does this archiving happen and in what order? And it turns out it is a very, very predictable process to within just minutes. So I know next month exactly when this page within minutes will be archived in the archive. So what is my attack? I will go in just before it's archived. I'll change the content. It will get archived. I'll change it back. And so now the archive that is a huge file has corrupted data. But if you go look at this, if you go look at the Wikipedia page, it looks normal to you, right? So this is what's called a front running attack, or what we've called a front running attack, to kind of just in time change the content before it becomes part of the archive. So this is another way. Now you don't need to necessarily control 0.1%. You can actually do this to all of Wikipedia and insert just kind of the right text. So this would be useful for attack like a universal trigger, for example. A universal trigger would be if I, like in a generative model, if I prefix my query with just the right sequence of tokens, it will always give me some answer, and only in that condition. And those kinds of attacks can take, specially crafted input. It would be quite easy to do if I could control all of the input to the model. Okay, so this is how to attack. By the way, Wikipedia was awesome. We also notified Wikipedia about this, and the response was like, "Hey, we're not a data set provider, but could you maybe tell other people, like, we're not in the business of providing cryptographic hashes alongside of all of our web pages, but maybe there are other ways you can tell your readers to defend against this." So I will detail the defenses here. Very simple. For the first attack, just you provide a hash. As a user, you verify the hash. And now 6 out of the 10 data sets are doing this. For the front running attack, we asked Wikipedia just randomize the order. That would prevent this. But if you are a user and this randomization is not happening, you can just sample the data set and compare, like, how different is my, hopefully you can get the 0.1%. If I sample 99% of my data set, I'll be able to snuff out the poisoning, right?
Or you could create the hash yourself.
Or you could create the hash yourself.
And then compare with the hashes.
There you go. Yeah.
Otherwise,
yeah. So the Wikipedia one's a hard one. It's a hard one to deal with. I want to pause here. Any comments or feedback from our online? Oh, I see Honey there. Hi, Honey.
Hey, how are you? Long time. Sorry, I couldn't make it to the office.
Oh, no worries. Okay, the next set of supply chain risk I want to bring up is in the model provider. So Microsoft is in the business of building their own. Other companies we work with or partner with are building their own. But actually, if you look across our customer base, so many of our even really mature customers are using third-party models. These are not mom and pop shops. These are huge companies that rely on some other company to give them a model that will be useful for them, right? So this is where the supply chain risk happens here. So how do I, first of all, what are the supply chain risk problems? Number one is that there are vulnerabilities in AI libraries. In fact, if you have downloaded PyTorch late last year, you probably saw in the news, it was actually looking at your etc passwd and uploading it to a researcher, right? This was the TensorFlow nightly build only. But there's this third class. So this first class, like vulnerabilities in libraries and in dependencies, actually there's a pretty rigorous process right now in information security to track these things. But on the right-hand side is kind of like not of interest yet to traditional information security providers. And that is that many of the serialization formats for machine learning models are actually, because they are serialization formats, you can have arbitrary code execution in them. And so many of you may have seen this, but it's really trivial to do this for Pickle. But you can also do it for PyTorch, for TensorFlow, for YAML files that all have elements of kind of like this. So if you haven't seen this before, first, I'm going to just play a little demo of what this looks like, maybe. Maybe not. Oh, here it goes.
Not sure we're sharing the.
Oh, is that sharing? Okay.
Yeah, we can try to reshare.
I can just talk through it if it's.
It's only presentation, Michelle.
Is that working? Okay. Okay, so Hugging Face is an awesome tool. I've been working with some folks at Hugging Face the last little bit about some of these supply chain elements. And in Hugging Face, essentially what a typical user does is they use the transformers library. Hugging Face has set a really high standard on creating a custom interface for models, and I love it. It's awesome. What they do is then you'll go search for some model at Hugging Face. You'll copy that model name and use it in the transformers library. Well, this model I put up now about a year ago, or not quite a year ago. It's called BERT Tiny Torch -Vuln. That should be your first indicator this is not a good thing to do. But when you load this model, it also opens a web page that looks like a hacker doing bad things for demonstration purposes. But the model itself, the weights are totally good. The BERT model is very usable. And if you think about this, I could have just as easily opened a silent backdoor or done anything just by using the model in its kind of native use case with the transformers library. We'll get back to slides. Here we go. Okay, so what I have been working with some of the folks at Hugging Face, and I actually, my old team at Microsoft has been working with Hugging Face also on some of these same things. So that's Matthew Maitre and folks at Microsoft. And what we discovered is that just on Hugging Face, let alone the other set of model repositories, there's lots of elements that include files doing popen, system, eval, exec. Some of these exist not just in Pickle or PyTorch files, but in YAML and TensorFlow, so that they're It's not just a one file format. There are suspicious imports like why does your model file need to have path access where it could create paths, for example, with the path lib, right? Also, some model files, I don't know why, but are using zlib decompress, which itself has a CVE in it. So it might itself be a benign use case, but it's presenting now this additional vulnerability because zlib is now a dependency. And another thing that I think is kind of funny is that Hugging Face is actually just GitHub under the hood, but it's even more. It's GitHub with large file support. So at Microsoft, I think the policy is you can't check in larger than 50 megabytes. At GitHub or at Hugging Face, you could check in 50 gigabytes if you wanted to. That's fine. So what people have done is they've figured this out and they're using it to host their music albums, random DHCP servers. And if you go to Hugging Face, at least a month ago, you could find 6,000 adware sites in the README files that they were just abusing the platform. All of these things present risk to somebody who might be browsing, looking for something, using a model on the platform. So as I mentioned, there's like this, there's this middle ground that so far is underrepresented in the supply chain risk management. So the traditional class of anti-malware and vulnerability scanners handle very well executables, scripts, macros, and software, but they do not care what is inside your model file. They do not look inside those, right? That's not in their purview. Most machine learning ops companies are doing a work and figuring out if your model is performing well, if it's ethical, but are they looking also at the additional security risks that come when you're inheriting that model? So in that middle area, there's just a few things. Hugging Face is doing a reasonable job at Pickle. Pickle Scan, Matthew and team released a few weeks ago, is a Microsoft open source project. Helps you to scan Pickle and PyTorch files. And then Robust, we're doing Pickle and PyTorch and TensorFlow and YAML and all of these things that we think is a gap in this industry. So just a quick demo. What does that look like? If I how do I make this actionable? Well, I can make this a DevSecOps thing where if I'm now, you can probably barely see this, but if I'm doing my transformers code, I can use, in this case, I'm using the robust intelligence tool to first I can scan the dependency and it will tell me, oh, there's a web browser to open it here. You don't want this. Or I can use this in like a context and prevent it from being opened. So this says with safe dependency checker as scanner, let me load this pre-trained model and it will fail because there's something bad in there. It won't let me proceed. So this is getting at the notion of just like SecOps for software development, bringing security closer and shifting left. This is now ML DevSecOps, where we want to bring this security right up to the developer who's using these tools. Okay, we're running out of time, so I'm gonna breeze through some of these things. I want to give you the bottom line up front. So if I've inherited a model, it also has, besides these software elements, it has this risk that comes because the model is imperfect or can be exploited by an attacker. And the bottom line up front is that there's a bunch of algorithmic ways to do this that are important and you should check. What's actually happening is not so sophisticated. And so that's kind of the bottom line up front, but I'll show you some use cases. So the algorithmic things, I think most everybody on this call certainly is familiar with kind of the different classes of attacks that can happen at test time to a machine learning model, but they exist in all of the three categories that we often break up security into. One is confidentiality. I can use an API to approximately reconstruct the kind of the mode of a class. A second is integrity, where I can evade For malware, I can check out a malware sample to evade a machine learning model. A third is actually availability. This was also done actually on the use case was for Azure Cognitive Services. This is Nicolas Papineau, University of Toronto, did the sponge examples where instead of optimizing the input for evasion, he optimized the input for query time, maximize query time. So this is like a denial of service for Azure Cognitive Services. If I give it a specific input, it will use the most compute, right? So very clever, very clever. All of these exist. All of them, what do they have in common? They're all algorithmic. They interact with the model, they query the model iteratively, and they figure out, they over time optimize an input to achieve a certain outcome, to compromise data, to evade, or to maximize compute time. So given that context, I found these statements quite interesting. These are academic papers, most of them, but these statements say from the National Security Commission in the US, this is a government-sponsored commission. They said this threat is not hypothetical. Andrew Moore at Google said poisoning has actually happened to me, right? The UK National Cybersecurity Center that we collaborate with, we were there just 3 weeks ago or something. They said these compromises, all three of them, confidentiality, integrity, and availability, have all been previously observed. And honestly, I'm scratching my head like, what do you mean? Have you observed this in a laboratory by researchers, or have you seen them in the wild? And my hypothesis is that it mostly, what we've seen in the wild isn't necessarily these algorithmic attacks. What we see is much, much simpler. So what I want to do in the few minutes remaining is quickly go through a few real attacks against machine learning models and use this rubric to grade them. Who did it? Like, what was the actor? Was it a white hat researcher, like me or you? Or was it an attacker in the wild? The specificity, was it actually attacking machine learning, or were they just, was it some software system? The intent, was this like, was I trying to prove a point? Was this like me uploading to Hugging Face, this demonstration script, or is there some kind of intent involved? And then sophistication, is it manual or is it algorithmic? And I've kind of already stolen the thunder. They're all going to be manual. So we often fear the AS actor specificity, intent, sophistication, that there's a nation state actor targeting like the military for tactical advantage using a sophisticated algorithm. But what actually happens is this. So Twitter. Twitter has a machine learning model that looks for abuse and for bot activity, and the bot's activity looks for similar content from different accounts. And it was evaded. How? It was evaded because somebody appended 3 random characters to the end of the tweet. And that was enough to evade this. This allegedly was by actually a state-sponsored actor in China for political intent. But the automation, there was automation, but it didn't appear to be, at least, sort of one of these algorithmic kinds of attacks. Another one in New Jersey, a man was accused of fraud by abusing the United States new service called ID.me, where you use face recognition to authenticate who you are, and you can kind of get your tax return this way through the IRS. And what did he do? He didn't do an algorithmic evasion hop, skip, jump attack. He actually changed the lighting and wore different wigs and created fake IDs. This actually, ID.me was unable to tell that these 4 pictures are actually the same person. So that's what the failure in the model was. This is just dishonest person. I don't think the person probably didn't know what machine learning was, right? The intent was just to get money and use wigs and lighting, right? Finally, this one I think is very, very clever. This is courtesy of some collaborators at Norton LifeLock. There's a whole talk will be at this on this one slide at RSA this year. But they discovered in their phishing detection very specific in attempts to evade machine learning. Evade the machine learning. Why? How do we know? It's because they're targeting features. If you'll notice, this particular anti-phish model looks for logos, right? It looks for keywords like password, and the attackers misspelled keyword. They changed the Office 365 logo. They obfuscated the O in Outlook. And in this Rakuten logo, they actually have the login and password kind of overlaying the logo. To a human, it might look normal, but now to like a screenshot, it's having a hard time identifying the logo. So these are sophisticated, but they're very manual. There's no algorithm involved here. So what is the point here is like, the point is that low sophistication does not mean low impact. Not using algorithm does not mean that the attacker can't achieve some interesting outcome. And I'm gonna skip this because we're running out of time. But what I want to point out is that if you look at all the failure modes that can happen to AI today, a recent survey by Katrin Gross said that of everybody surveyed, all the incidents that happen to machine learning, how many were actually an attack? It was 5%. One out of 20 maybe was an attack. The rest were unintentional failure modes, things that happen just because models are brittle and fail for other reasons. So I'm zooming back out here. Why do we at Robust Intelligence focus on holistic risk? Security is very important. It's a 5% piece of a pie about other kinds of failure modes. And this is why we are, focusing especially on, the way things can fail has changed dramatically just in the last year, as you well know at Microsoft with the advent of large language models, which is why in our platform, we're also providing ways that we can look at generative AI outputs and how to measure those for these three areas of risk also. What would I do if an attacker were present? How would that interact with my generative AI system? How would I check for bias and fairness in a generative AI system? So this is kind of where the future is in this space. Is we have a kind of obligation at Microsoft, at Robust Intelligence, to measure and mitigate and reduce these kinds of risks that happen in the supply chain. The future is that very few people are going to roll their own large language model. They're going to inherit from somebody else. How do we reduce those risks? Very short plug. If you have friends who would like to know more, Ram at Microsoft and I have co-authored a book that's out in May, to which all author proceeds go to charity. This is a non-technical book meant for decision makers to make them aware about, hey, I want this, I want this AI in my bank. What could go wrong? This is a book about that. It tells stories and will hopefully raise awareness about this topic. So that is it. I thank you for having me today and would love to discuss more of this either in person or offline.